The only way to learn something, in my opinion, that generalizes into the future is if that pattern repeats itself into the future in some way. An inductive bias is just the set of everything that you know before you start learning something. You have to be humble enough to ask the stupidest questions and look stupid. If you can do that, that'd be my number one recommendation to people, is just ask. The only way to do something new, in my experience, because if you try to kind of jump into the full complexity of the thing that you're interested in, it almost never works and you get frustrated and lost.
So, welcome to Curiosity Is, the show where we explore what drives brilliant minds to push boundaries. I'm River, and today I'm joined by Dr. Andy Keller from Harvard, whose work bridges machine learning and neuroscience in some truly mind-bending ways. And to kick off the show, I've asked Dr. Keller to explain what curiosity is to him.
Thanks. Yeah, thanks for having me. It's a real honor. I would say to me, curiosity is that extra experiment that you run at 3 o'clock in the morning, which is, wouldn't it be incredible if this worked? Just before you go to bed, and then turns out, who knows?
I'm sure you have a ton of those.
I mean, they're rare, but I have a ton of experiments. Most of them don't work.
Is it like juggling a bunch of, like, does your mind have to be in a lot of different places to be able to actually make progress? Do you think you have to be testing out, like, maybe even competing directions?
I think that's a good way to put it. Yeah, I think for me, it often happens. I go in a more or less kind of linear path with backtracking. So you'll follow some idea for a while, and then you just are really not getting anywhere. And then at some point you say, okay, let's go back 5 steps and try something new. And that's typically what happens at 3 a.m. when you're deep in some rabbit hole, and then you kind of try one more thing just to see, and then suddenly, like, oh, something's working.
Do you remember one of those moments where either you or Dr. Welling came up with the idea for neural wave machines?
Actually, yeah, I think I do. So, yeah, Max was talking a lot about networks of coupled oscillators, and from the physics perspective, often telling me in our meetings, like, everything is a harmonic oscillator in the universe. Quantum mechanics can be described in terms of networks of coupled oscillators and so forth. And so I had this kind of on my mind, and I was sitting at the hair salon, actually, and I remember going on Twitter and seeing a paper about coupled oscillatory recurrent neural networks and the fact that they had this global coupling to them, and thinking, I bet if we just make that global coupling local, we would get waves in this latent space, and then we could do interesting things with that. And so, yeah, came home and tried it, and it started working immediately. So that was one of those moments.
So, what does it mean for something to be coupled and for it to be either global or local?
Yeah, so I guess that's I think a really, maybe a deep question. Uh, l- uh, Coupling just kind of means that there's some interaction between the parts of a system. So if they're uncoupled, maybe there's absolutely no interaction. You have two things sitting in a vacuum far apart from each other. Um, in terms of like a network of coupled oscillators, you can write, it's a very simple equation, and you can write down, and basically it's like, if the equation of motion for one oscillator has a term in it which depends on the position of another oscillator. So if my acceleration depends on this guy somehow, that means they're coupled. If there's no terms and they operate independently, they're
Okay.
uncoupled. And so in a network of coupled oscillators, you have more than just two. You have maybe 100 of them or something. And so how you define which one gets influenced by which other one is, yeah, it's either global or local. If it's local, you imagine you lay them out in some space, and then you say, this neuron or this oscillator can only be influenced by guys that are within a local region of it.
Are there patterns that emerge from local relationships that are observed but do not look the same at at the global scale? Or is there like maybe not symmetry, but like some kind of like fractal quality where uh, independent of what scale you're looking at, the local and the global landscape look the same?
Yeah, so that's a fantastic question, and that's a property of systems that are near a critical point, or so it's like this. The definition of criticality in the dynamical systems literature gives you this what they call scale-free property. So I'm sure you can look up videos of this phenomenon where if you zoom out, you'll have some system that has maybe black and white patches to it, and you keep zooming out or you keep zooming in, and it always looks the same, kind of like you said, like this fractal property, and that's a function of the type of system that you have. Um, yeah, in our models, we definitely don't have this scale-free property just yet, but it's something that is, in some sense, observed in the brain, and so it is really interesting to think about building models with that property, and that property also implies a lot of things about how well information is transmitted over distances and yeah, other types of computational properties which may be beneficial for a neural system.
So when you're working on these projects, there's obviously some inspiration that you draw from biology, as maybe like how information can be represented. Um, how actively are you pulling from biology, or is it more of like you're looking at abstract patterns in biological systems, not necessarily things that are, I don't want to say fundamental to the biology, but that are an intrinsic property to it, rather than maybe say like an emergent
Yeah.
property?
Yeah, right now in the past I've been looking a lot at these abstract properties, just because those are ones that are easier to build into artificial neural network systems in a way that still maintains computational efficiency and the ability to train it with backpropagation like we typically do. So that it gives us that benefit. It also gives us the benefit of looking from the physics perspective of like saying, okay, this is just an abstract mathematical property which somehow relates to something that we see in the brain. Um, what do we know about it from physics? How can that maybe inspire us to think about how this could do some sort of computational property in an information processing system? Um, but that being said, now I'm starting to get more into looking at very specific biophysical properties of neural systems that we know about. So, like one of those is the distribution of these horizontal recurrent connections in visual cortex. And it's known that they follow a very specific distribution. So, like neurons that are selective to one specific type of stimulus, like a line that's vertically oriented, might also or are more likely to connect to other neurons that are selective to the same stimulus than they are to other types of neurons that are maybe selective to lines at different orientations. Um, and so this is a specific pattern that we've observed in the distribution of these recurrent connections. And so I have theory of like artificial neural networks that maybe explains why this could be beneficial computationally. And so these are the types of things where it connects more closely to the biology, but again, it's yeah, still not even close to what some of these uh, I'd say real neuroscientists do. I'm a fake neuroscientist.
Oh, and he's humble too. Um, do you think that biology is like how analogous is biology to data? How integral is data structure to biology? I know those are two different questions, but I'm just kind of fielding it out as you know a particular thread that might help elucidate either of those points.
Maybe it depends on the type of data that you're talking about. I know a lot of I know very little about biology to be completely honest. Uh, so the data does seem to be a large part of what we like know about biology. It would, when we're trying to, if I'm trying to make claims about a biological system, I really need to match the outcomes or the predictions of my model to the data that has been recorded from that system. And there's really no other way of validating the claims that I'm making. So in that sense, then I think it is very integral and very important. Um, but to be fair, also my work has not done too much of that yet. It's been more kind of on the theoretical side of let's take this, like I said, take this abstract property and see how what we can do with that.
Can you tell me about a little bit about what the direction that your work is going in these days? Like, what are some of the things that keep you up in the middle of the night, like the unsolved questions that you want to answer that you think would be integral to being able to take next steps?
Yeah, I think the most exciting thing for me. So, like I've said, my work has been a lot inspired by these like spatiotemporal dynamics in the brain. So, traveling waves or these patterns that you see in networks of coupled oscillators. And what I've been trying to figure out is okay, is there a computational role for this? Does this play some role of an inductive bias in natural systems? And what could this be? I think one of our hypotheses has been that this is kind of what I started my PhD on was um, maybe this plays the role of a bias towards learning structure in the data, like symmetry structure from the world. And when I say symmetry, I just mean like it's just a way of describing the organized structure of the world, but in a way that is like repeating patterns. Maybe that's the way to think about it. Like the only way to learn something, in my opinion, that generalizes into the future is if that pattern repeats itself into the future in some way, right? So the big question for me has been okay, how does the brain learn these symmetry structures, whether they're over space or over time? How can this be done? And yeah, we think that waves play a role, and I'm starting to formalize that more and more. This a recent paper that I've just submitted is doing a bunch of the math for that. And like I said, I think that also may explain some connection properties of visual cortex. So that's the stuff that's been keeping me up. And there's a lot of questions of how that could actually be implemented in a biological system, which are not problems when you're implementing it on a computer, which I think are also really challenging and very interesting questions at the same time.
You mentioned symmetries and inductive biases, and I just want to know if we can dig into those for a moment. Um, how would you explain it to a 5-year-old?
I'd say an inductive bias is just the set of everything that you know before you start learning something, right? So it's like imagine I'm asking you, I give you a set of numbers and I'm asking you to predict the next number. So I give you 2, 4, 6, and then I ask you, okay, what is the next number? Uh, you're most likely going to say 8 or something like that, right? Um, but there's actually no reason
Mhm.
why it has to be 8, right? It seems like that's the most likely thing because it seems like the procedure is a set of even numbers that I'm
Like assuming that there's a pattern to follow in the
right.
first
Yeah.
place.
But that pattern doesn't have to be even numbers. It could be the set of all numbers except for 1, 3, 5, and 7 or something like or 1, 3, and 5. And then in that case then the next number would be 7, right? It's just that that pattern is in our
Mhm.
minds much less likely because that's a much more complicated pattern than just saying the set of all even numbers. So the this idea of simplicity is an inductive bias that I think we have um, when we are trying to figure out rules that govern the observations that we're making or when we're making predictions. And there's
So like Occam's razor would be an inductive, not maybe not itself is an inductive bias, but um, our it's a fallacy to try and assume that things that are simple are inherently better explanations for how the natural world works.
yeah, well, yeah. I mean,
Maybe
It
not
could be a
fallacy, but
fallacy. Who knows? Who's to say what's correct? And so I think the idea of an inductive bias is um, you just have to pick one. And if that one happens to match the data that you're observing, you'll do better. And if it doesn't, you'll do worse. So this is the whole idea. And I think that nature has kind of built a set of inductive biases for natural systems which match the natural world and make learning systems more efficient in the natural world. Whereas we have a few core induct I mean we have many inductive biases in our systems right now, but largely they're very over parameterized, super flexible systems. And I think that causes them to learn a lot of these kind of weird solutions, shortcut solutions, and they generalize in these very weird ways that we're not expecting.
okay, so it's like if you overfit the data and then you're not learning patterns in the population, you're learning patterns in the sample.
Yeah.
Is
Yeah, you
sounding
could
about right?
that's definitely one way to think about it. So yeah, in Occam's razor can be exactly an inductive bias. And a lot of times in a neural network model, you impose something like that to some extent through you had weight regularization, right? So you had an L2 norm on the magnitude of your weights. You penalize your model for how big its weights are. So I say I want my model to learn the simplest possible solution to whatever my task is. And that's a choice of inductive bias. It could be that that's not the right choice, but generally that we tend to see that makes these models generalize better.
And thanks for breaking down inductive biases. I'm curious if you can also now break down symmetries. I know that in prior talks you'd mentioned that they're perhaps the most natural decompositions of the world, and it sounds really interesting. I feel like if I could better understand that, it would really give me a better view into what's going on when we talk about your
Yeah.
work.
So I think a high level definition of symmetry is just so I would say instead of trying to define symmetry itself, I would take an alternative phrase and say something is symmetric with respect to a given transformation if that thing doesn't change when I apply that transformation. So my face is roughly symmetric with respect to these mirror flip transformations because it roughly doesn't change if I do a mirror fold over the center line. And similarly for different shapes, circles have this radial symmetry. I can do a rotation of any amount and the circle stays the same. Um, so it's generally just this idea that it is the properties that stay constant of a thing despite you doing some sort of transformation to it. And I think when you start to think about more complicated objects, the value of symmetry is to say like some part of that object stays the same despite the rest of the world around me changing. So my the essence of Andy, the Andiness of Andy stays the same despite the fact that I have a new shirt on or my hair is longer or looks terrible because I haven't washed it in a week. Um, those types of things I think are how I tend to think about symmetries is just transformations that leave the underlying essence of the object the same. And so if we think about the world and we want to learn about objects, if I can learn about a like a pencil and I say what are all the possible things that I could do to this pencil which still keep it a pencil but change all of its different properties, and if I can separate those things out, then I only need to see one image of a pencil, or I only need to just like see very few images of pencils to understand that this thing that I'm looking at right now is a pencil, despite all of the different possible transformations that could be applied to it.
So, in the context of neural networks of whatever kind of structure, the symmetry would be, or symmetries would be encoded in a particular like layer of the network. Um, and so like that network layer would be responsible for identifying this property of whatever it's being exposed to.
Right. Yeah.
So is there a limit to how many symmetries there might be stored in a given network? And are they like, is it like a zero sum game when it comes to trying to train a better network that has better intuitive reasoning
That's a
skills?
great question. Yeah. I think practically um, implementing these things, we're probably going to come up with better ways to do it in the future, which makes it less kind of zero sum, so to speak. But right now it definitely is. So uh, every kind of symmetry you add in incurs more memory cost. Uh, and you only have so much memory on your computer, so you can't encode a million different things.
When you're saying memory, you mean like uh like RAM, like currently being used memory, not like the memory used to store the weights of the size of the network stays the same, but not maybe not stays
Yeah.
the same, but
Yeah, the trainable weights
yeah.
of the network typically remain constant, so you don't have more parameters. But typically with these equivariant networks, which are networks which have these symmetries built into them, like you said, you have a multiplicative increase in the number of activations of your network. So that's where, yeah, the RAM
Mhm.
required to compute your forward and your backward passes ends up increasing.
And so do these symmetries, do they have an interpretable structure when you're looking at a network?
Yeah, I guess this.
So like if you were
No,
to
sorry.
like if you were to model a network just visually, like or graphically, and you were to display each layer of the network, that I mean, for me, like seeing it visually would help. So this particular symmetry could be narrowed down to seeing activation here when a given like category of input is given, and with there you will definitely see that particular, let's say, call it a shape, emerge whenever you have this. So is that a property of the network, or is that a property of the input that it's able to elicit that response
Mm.
from the network? Or
Yeah, I'd say it's a generally a property of the network. So you build in these symmetries to the weights of your network.
oh, you build them. They're not like
Well, the goal
learned.
is ideally we'd love to learn them, but right now most work builds them in explicitly. But yeah, my
Okay.
that was my dream. If you're asking me like what my dreams are, it's learning symmetries from data. Um, but yes, I think the simplest example of this, which probably helps a lot, um, is a convolutional neural network. So a convolutional neural network has this symmetry with respect to spatial translations of the input. So the network will process the input the same whether the input is in the top left corner of the image or the bottom right corner of the image. It's just that your output, so if you think of a convolutional neural network, it's applying the same little feature detector everywhere in the image, and the output of that is some feature map. So that's, like I said before, it's a set of activations which are in some sense duplicated over all of the elements of this translation group, over all of space. So instead of just having one activation where I say I'm looking at, like an MLP would say, I just look at the input and I map that to like a single output. That's my activation. Now I'm saying, no, I want an output everywhere in space. So I want to take my same filter that I learned before and apply this everywhere in space. So now I have this feature map. And like you said, if you want to just visualize what the symmetry is doing, well, now you have that. You have this feature map, which is saying like, look, if I move my input here, the corresponding activation in this feature map is also translating. It's moving in space in this way. So it's really preserving this spatial structure of the input, and that's the maybe the simplest example of building a symmetry into a model. But the same exact idea extends to rotation and other group transformations, pretty much any continuous group transformation.
So waves would be themselves symmetries because during the period of the wave, it returns like no matter what the phase of the wave, you're still gonna have the period. You're still gonna have the amplitude. So that those are the intrinsic properties of the wave, which would mean that they're also the symmetries
Yes,
of the wave.
absolutely. Yeah, so and that's a property that we even use in some of these models, and it's something that has was inspired by I'm not sure if you're familiar with this idea from Jeff Hinton called capsule networks. The idea being that you have a network, or your neurons in your network don't just have a single activation. They have an activation that lives inside of a capsule, and the capsule kind of represents all poses of an object simultaneously, but the magnitude of the activation of that capsule, kind of like the amplitude of the wave, captures the presence of that feature. So it's saying like all of my neurons that correspond to a hand are going to be in one capsule. But then depending on how many fingers I'm holding up, it's going to change where within that capsule I'm activating. So kind of like the phase of the wave. But the magnitude of that capsule is always going to be the same. So I'm always going to know my hand is there. It's just depending on the phase, it's going to tell me how many fingers are being held up.
Okay, so then the capsule also captures information not just about the state of an object, like that there's the presence of an object, but like the state
Yeah.
of an object. But then that means that the state space for that object has to be defined. So if it's presented like with a new, let's say it's only seen like hands like this, but it's never seen a hand that was, uh, making a new sign, like that would not be captured in the phase space. So would that still mean that it is a hand?
Yeah, that's the crucial point, I think. I mean, that's why it becomes very important how you define what the decomposition of the world is into poses and parts. So what is a separation of things? And from the physics world, this is where people seem to say, yeah, it's these group transformations, which we can think of as symmetries. And I think for a lot of the visual world that makes a lot of sense. So any kind of smooth, continuous deformation, you want to represent as like that is the same thing, um, until you kind of
Like a donut versus a like a
yeah,
mug.
yeah. I
Like as long as they're the same topologically, then they are the same concept
I think to
tractally.
some extent that's the idea, but then obviously if we look at a donut, we can tell the difference between that and a mug. So there's there's a fine line there. But I think yeah, something like that is on the right track.
I'm curious, from what I've been able to see working with like large language, not working, but like, using large language models, um, it seems that being able to generalize beyond training data is really big obstacle and being able to go beyond just pattern recognition. Do you believe that integrating new structures into neural networks will be able to help break us beyond this current paradigm, and take us to generalizability? Um, or do you think that ultimately it always boils down to whatever symmetries are built into the network? Because as I understand what you've been saying, uh, we're limited by the symmetries that we have, but maybe there is a structure that we could allow a network to develop its own symmetries that it identifies in like a unsupervised kind of
Yeah.
approach.
Yeah, I think you've hit it right on the head. That uh, is what I believe to be the way to fix this problem of generalization, I call like strong generalization beyond your training set. Whether those need to be learned from the data or how, I think they do need to be learned from the data to some extent, but how you do that is, I think there are many different ways. So one of them could be that, and some people have tried this already. You really just say, okay, yeah, I want to learn the structure of my network, maybe through something like meta learning or through some like evolutionary algorithm, or I parameterize it in a really tricky way. And then you kind of sometimes it works. I think the alternative, which I'm interested in, could be you build in a set of symmetries into your latent space, but then you allow the network to learn the mapping to that latent space. So even though you have a fixed set of symmetries, what those mean is determined by whatever you map from input to that space. And so that's a way of kind of repurposing these fixed structures for whatever the task is that you observe. And this is something that Elafit at MIT has kind of pushed a lot in the context of like grid cells and place cells and hippocampus. This idea that those systems serve as like a scaffold, and those have a specific algebraic structure to them, and you can kind of use that to pin things onto that and then kind of move around in this abstract space.
I want to build off of what you're saying there, and kind of take us in a little bit of a different direction. Because when I'm hearing you talk about these structures, I'm like approaching it from like a biology first kind of perspective. But you're approaching it like from the data engineering side into biology. And I'm curious, when you're learning about the systems that you're trying to model, what kinds of clicks do you get where you're like, "Oh, wow, this is just like this." Like in a way, I guess I'm trying to get at, do you think that you're able to predict features of biological systems using the knowledge that you have from the computational side? Like that your computational perspective, do you think that gives you insight into biological systems? Because if so, I think that speaks to some, I maybe call it a symmetry between biology and abstract data.
Yeah, I would say I think there definitely is the possibility to do that. I don't know if I would say that personally I can do that. I think it's often challenging.
Not
Not
yet,
yet.
maybe.
But I think that's definitely something that I aspire to is this idea of thinking about the brain or biological systems in terms of these abstract computational principles or dynamical systems principles, and I think there are examples where this has worked out in the past. And I was at this workshop recently in Toronto organized by some people from Western, Lyle Muller, a collaborator, and some others, and someone gave a talk there on predicting insect behavior in when they're in swarms or in like flocks of birds or swarms of locusts, and you can model those with relatively simple dynamical systems, and you can actually predict kind of where they're going to go and what's going to change. And then they were able to get this down to like the individual insect level, where they just like put it on a, I think it was flies, they put them on in like a corridor with a single trajectory where they get to a decision, or something like they're walking straight down and there's two kind of doors at the end, and the fly has to make a decision of which door it's going to go to. And they basically have a model that kind of perfectly predicts where this fly is going to go, in a very, very, very controlled setting. But I think in these types of systems starts to become clear that at some level, yeah, the physics takes over, the dynamical systems approach takes over, and that gives you a description of the system at a higher abstract level.
Like if there is some underlying structure that the biology has to, maybe not necessarily it has to, but it tends to fit because that structure has some property about it that uh, is good for organizing information at
Yeah,
scale.
absolutely. And I think um, we could maybe say that we already kind of took inspiration from that, or leveraged that insight already a little bit with like spikes and spiking neural networks and McCulloch-Pitts kind of artificial neurons, um, and thinking of these spikes as kind of binary on off, even though there's much more to it than that. But like thinking of it like, okay, maybe this is just a bit of information, and then kind of extrapolating from there. And what my
Hmm.
work is thinking that maybe these kind of larger spatiotemporal dynamics, which we see throughout the brain, waves and coherent patterns and oscillations, maybe these are also a information processing principle.
So you work in digital like learning, right? The networks that you're building are obviously digital systems. Do you think that you could I'm not sure what there is out there right now for being able to work on like analog neural networks or how you would simulate analog in a digital format, other than like physically building some kind of contraption that, mirrors what you're trying, like your traditional like, MLP. But do you think that there are ways to model analog systems in digital to be able to replicate it precisely or accurately? And do you think that that information gives you insight into uh, the data that underlies it? That's not maybe the best way to phrase that question, but I'm just curious, like how, like the to get from point A where we're at digital to point B, we have to, which is analog, we'd have to like do some, there has to be some like gap that we're closing, and then given having closed that gap, what insight do we get out of that, regardless of what it we have to do to close it?
Yeah.
Like, does that make like
Yeah. No, I
yeah.
think that makes a lot of sense.
Um,
I think so. Maybe I'll say at the highest level, uh, the way to simulate these analog systems on digital hardware is currently very inefficient. So you can do it, but you cannot build anything near the same level of complexity that we can build with these kind of artificial neural MLP type structures that we're building right now. And they also be
and that's because you have to like simulate each like slice of
right.
time, which just increases the load of like
Yeah, or you
calculation.
can use these really fancy ODE solvers that kind of help you a little bit, but still you're going to incur significant penalties. Um, so that's I say this the biggest limitation. People do build analog hardware right now, and that's like in the neuromorphic community. I'm not an expert on that, so I'm not gonna embarrass myself by trying to talk too much about it. Uh, but I think that's a super cool field. I just know that there's still limitations to that as well in terms of how big they can be and how you train these types of models and what you can run on them, how you program them, and so forth. That being said, I think there's a tremendous amount we can learn from just even these small models and simulating analog systems. Um, I think the challenge is how do you translate what you've learned there into maybe a digital framework so that it's useful. I think that's still hard. For example, say you learned that you have this analog system that has two sinusoidal patterns, and there's some crazy like cross frequency coupling going on that's causing some frequencies to die down and other ones to go up, and this allows you to transfer information in an interesting way. How do you take that and say, okay, now I'm going to discretize time. I no longer have phase. I no longer have frequencies. How do I build these things back in? Maybe you have to use complex numbers, or so it's like these things are not impossible, but it is the math starts to get complicated, and but I think just playing around with the analog system, sometimes you get these insights of like this is how this thing works, and so we should try to do something like that.
When you come to like a roadblock in something that you're trying to understand and you feel like you're out of your depth, how do you tend to try overcoming that? Do you rely on like an external partner, or do you try to undertake learning the context and working it on yourself, or like, because as a scientist, you're collaborating with other individuals, and I'm curious how much you need to be able to know yourself in order to be able to work independently, even if you are collaborating with other people, I guess is a better way to put it.
Obviously, if you can talk to someone who knows the thing and they can guide you through it, that's the best possible option because you can ask them questions, you can clarify. I mean, you have to be humble enough to ask the stupidest questions and look stupid. But that's really such a blessing if you can do that. That'd be my number one recommendation to people is just ask the dumbest questions you can. If you don't have someone, a lot of times you'll be working on something where your advisor doesn't know it, or your collaborators don't know it, and you have to figure it out still. And sometimes even I haven't known enough to be able to even read the relevant like Wikipedia pages. Like you look at it and the words are there, but it doesn't make sense, or whatever you're googling doesn't make sense. ChatGPT is spitting out garbage. So in my experience, then the best path forward has typically been try to go back to the simplest possible examples of the thing that I'm trying to do or understand, and like work through them by hand, either like on paper or on a computer. So like literally implement the thing that I think should work at the simplest possible level and slowly build up from there. That's really the only way to do something new in my experience. Because if you try to kind of jump into the full complexity of the thing that you're interested in, it almost never works, and you get frustrated and lost.
And since we are closing up on our time, I wanted to know if there was anything else that you wanted to share about how your curiosity has like led you through your academic journey.
Yeah, I'd say it's what has kept me excited about doing research and kept me wanting to do research. I think without this kind of curiosity driven research, where it's really like I am trying to do the craziest thing I can think of. Maybe not the craziest thing I can think of, but it's like I really have this idea of like, wouldn't it be crazy if this thing worked? That really gets me excited, and it's what motivates me to continue working. And when I have students, that's what I try to instill in them, is this like motivation of like, wouldn't it be so cool? Like this is the cool thing that we want to do, right? Like I think that's maybe the most important part about it, because you're gonna hit things that don't work, and yeah, it's pretty frustrating and sometimes isolating to be working on a project that doesn't work and nobody is interested in. But if you still in your mind think like, yeah, this is a cool idea, I'm excited about this just on its own because it would be cool if it worked, then that's like, what more can you ask for, right?
Awesome. Thank you so much for taking the time to speak with me today. It's been incredibly enlightening. I know that I fumbled around asking a lot of the dumb
No, this is great.
questions myself, but I really, really appreciate it. Thank you so
Yeah, thank you
much.
so much for having me.